Yeah, so welcome again to the lecture course on quantum gravity. So last time we have discussed quantum geometrodynamics. What's that? This is the canonical or Hamiltonian approach to Einstein's theory of general relativity and the quantization, according to the usual more or less heuristic methods that we use also in quantum mechanics. Identifying the P's and the Q's, imposing on them non-trivial commutation relations, identify the Hamiltonian, and so on. Now the most important thing is that we have to deal with constraints. I mean, this is not what you usually have in quantum mechanics. Constraints, the Hamiltonian constraints, which is one local constraint, and the momentum or diffeomorphism constraints, which are three local constraints. And we quantize them in the spirit of Dirac. That is, we formally translate all these variables into operators and act with them on the wave function and demanding that it be zero. I mean, the classical constraint is zero, and now the application of the quantum version on psi is zero. Now, what is psi? Psi is a wave functional, because it depends on functions, and we have identified a dynamical variable, which is a three-dimensional metric, HAB. AB goes from 1 to 3, and also x, to save writing, I just write x, but I mean x1, x2, x3. And of course, you can have other fields, non-gravitational fields. People usually just call them matter fields, but it can be the electromagnetic field or maybe a quark field, whatever. In most applications, we use the simplest non-gravitational field, which is just a scalar field, phi of x. But of course, you can do more complicated things. Note that this wave functional is independent of the lapse function and the shift vector, which are also part of the four-dimensional metric. The four-dimensional metric are 10 components, 6 of which is a three-metric, and 4 are in lapse and shift. But lapse and shift somehow only give you the information classically where your hypersurfaces are, the three-dimensional ones, and what the coordinates there are. So they have no independent dynamical information, and this is why the wave functional only depends on the three metric. So as John Wheeler said, so the three geometry is the arena of quantum geometrodynamics. So that was the insight that people in the 50s, 1950s, 1960s got. Let me write down again these constraints, because what today we do is not doing continuing with the general discussion, although there are still interesting topics, but making semi-classical approximation, and in particular showing how time, which had disappeared at the fundamental, re-emerges as an approximate concept from these equations. So let me write down these equations. For the time being, I insert all units. So then we have minus 16 pi g over c to the 4 h bar squared. And then we have this kinetic term. So that's what substitutes the minus h bar squared over 2m Laplace in the Schrödinger equation. So that's a de Witt metric. I don't need it here now, but it depends on the three metric. And sometimes people write these quotes here, which means that there's a factor ordering problem which is not solved at that level. So I have no time to go into that. This has to do with regularization of infinities that occur in field theory. But fortunately for this topic, we don't need to go into this. Okay, this is the kinetic term. Then we have the potential term. And this acts on psi, of course, and we don't want to restrict ourselves to vacuum, so we introduce here a Hamiltonian for the matter field. And so we have here some operator H orthogonal matter on psi equals 0. So recall, this is the de Witt metric. And yeah, and here we have explicitly constants, and I took some care to insert them because we need them for the semi-classical approximation. In particular, one of the scheme is to make an expansion in powers of the gravitational constant. So assuming that G is a small. Okay, G has dimensions, so of course one must say with respect to what it is small, but some heuristic meaning it's small. So as sometimes you take c, the speed of light, to be large or h bar to be small. Yeah, this is called the Wheeler-de Witt equation. I write in the following just WDW equation. And then this is one local equation. I mean, all these things depend on x, so I don't write this always explicitly. And then we have three others, the so-called momentum constraint, 2I h bar dB HAC, and then we have d psi over dHCB plus HA matter on psi equals 0. So these are the momentum or diffeomorphism, where diffeomorphism refers to three-dimensional diffeomorphism, three-dimensional coordinate transformation constraints. So these are the central equations. So these are the equations you have to live with if you're doing canonical quantum gravity. And these are the equations also we will then expand to get back Einstein's theory plus corrections. So that's the Wheeler-de Witt equation and the momentum constraint. So please note that here in the momentum constraints there's no gravitational constant, also no speed of light and something, just the h bar. So here in particular no g, which means that they have a different status as here. So if we expand equations in the gravitational constant, this is very trivial because at each order this is the same equation. It just has to do with the fact that this is purely kinematic in a sense, just giving you the freedom to have coordinates on the 3 surface and not so much the dynamics. Okay, so how do we proceed? Because at the end, this is where the success relies on of this. Yeah? So you must have, I mean, in a physical theory, in a new physical theory, you must achieve the following two things. You must have a consistent framework, and you must consistently build a bridge to the known physics. You must embed this Einstein theory and also quantum field theory on curved space-time into this, like Newton is embedded into Einstein. And second, of course, you must have also an understanding of how observable effects are calculated. And I will show you at the end, how this is done, and I will present you one potentially observable effect that is unambiguously derived, but still too small to be seen. Yeah. And to make the things clear, I will now spend maybe even most of my time by discussing an analogy from quantum mechanics. Now, this is something that you also find in quantum mechanics books, maybe not in the way I present it, but in related ways. And then we translate what we have achieved to this case. You will see why this can be done. Because in the quantum mechanics case, first, it's interesting by its own, even if you're not interested in gravity, but you're here because you're interested in gravity. So you will see what is going on in a much simpler framework. So we have here the analogy from quantum mechanics. So I just write QM. And this is a mixture of two approximations that is, in a sense, everyday life for many quantum mechanics physicists, namely the Born-Oppenheimer approximation and the WKB approximation. So we use a mixture of the Born-Oppenheimer, and the following I just write BO for that, and WKB approximations. Now WKB is already an acronym, but it's a standard acronym. It stands also for three people who in the 1920s did that first: Wenzel, Kramers, and Bruin. Sometimes a J is added. No, I forget for whom it stands. Maybe has done later work also. And yeah, so WKB is what is usually this you call the semi-classical limit. Maybe this is what you or should have learned in your quantum mechanics course. Born-Oppenheimer is something that people in quantum chemistry and so use all the time. What is that? That is a scheme that is based on the observation that, say, in a complex nucleus, for example, you have different scales. Namely, you have the heavy nuclei and the light electrons. So, because in general you cannot solve the Schrödinger equation exactly, analytically, you can either do numerics, but otherwise you can make an approximation scheme where you make an expansion in a parameter that has the ratio of the electron mass over the proton mass in the expansion. And then you can actually achieve go quite far, achieve interesting results. And this is what first, Born-Oppenheimer published already in 1929 when Oppenheimer was postdoc in Göttingen with Born. And it's since then a standard procedure. Now the idea here is to divide up a total system into two parts, into two subsystems, so to speak. And many things rely on this, in physics generally, rely on this possibility that you can divide up a system into subsystems. That is, you must have a priori knowledge, of course, of your system and identify what are electrons and what are nuclei, and that. This is knowledge that enters. You cannot expect that this comes out. So divide the total system into two parts. And these two parts here, in my example, I do the simplest. I describe this by two configuration variables, a capital Q and a small q. And you can, this is one-dimensional, but you can add here indices a from 1 to n. The whole thing goes through. You just would have to add all the indices and summation. But it's not my point to make it most general. My point is to make it clear. No? So we have here these two, and in the molecular case this corresponds to the nuclei and this corresponds to the electrons. More generally, these are so-called slow variables or heavy variables, and these are the so-called fast or light variables. Because they are light, then they move faster, in a sense is connected. In our case, then, gravity will play the role of this slow or heavy part, basically because the Planck mass is much bigger than masses that you have in the other sectors. So gravity will then, in our analogy, play the role of the capital Q. But now we are just in quantum mechanics, so not in gravity. And in quantum mechanics, of course, we want to solve the Schrödinger equation. And here we want to solve the stationary Schrödinger equation because this is analogous to the Wheeler-DeWitt equation, because there is no time. Also in the stationary Schrödinger equation, there is no time. So we have h of psi of small q and capital Q is E times psi Q and Q. No? So very simple. In the Wheeler-de Witt case later, this energy here has to be set to 0, no? Because you have here then on the right hand side just 0. So this, as I explained last time, this together gives the Hamiltonian for gravity plus matter. And acting on psi equals 0, so there is just a 0 on the right side. So in a sense we have a type of stationary Schrödinger equation with energy 0. But let me do it here with energy E, because this is quantum mechanics, and the important thing, there is also no time here. Okay, so the Hamiltonian is then the usual one, d squared over dq squared plus v of q. Okay, so this is the heavy part, and then we have, in a sense, the rest, the light part, but also the coupling. No? I write it here as a small h, so these are the electrons and the coupling of the electrons to the protons, for example. So these are, for example, the nucleus, and these are, for example, the electrons plus the coupling to nucleons. We do then the following ansatz. So far, this is general. So the ansatz is that for the solution psi, which depends on q and capital Q, you write this as a sum of states, chi n of capital Q, psi n, q, and q. Okay, so far this is just formal. I mean, you must say what these things are or should be, and we demand that this, okay, this only depends on the heavy part. This here depends on both, but we demand that this fulfills the normalizability condition. So we demand that this fulfills, I mean, that psi n over psi m is delta nm for all q. I mean, these are electronic wave functions, but they also depend on the nuclei, on the position of the nuclei. But this inner product is the integration with respect to the small q. So integration with respect to the small q. The inner product with respect to q. Now in the gravitational case, this small q will be the non-gravitational part. And for the non-gravitational part, there's no ambiguity in the inner product. I discussed the Hilbert space problem earlier, because for the full quantum gravity, it's not so clear whether you use the usual Hilbert space product or another one. But the point is here we do not need to solve this ambiguity, because here only the inner product here in this sector enters. And there we agree that we can use the usual L2 norm. So, okay, now we insert this ansatz into the Schrödinger equation. And I may allow myself not really to do every step, but you can read every step in the book, or you can, as an easy exercise, do that. But I explain what is to be done and what is to be inserted where. So we insert this ansatz, insert this ansatz into, let me call the Schrödinger equation star, into star, and perform from the left a multiplication with the electronic functions psi m and integration over q. No? So you insert this, that it's very simple to insert this here, and then we just integrate from the left over the small q and multiply by this, which means that the small q is away, and also the psi's are then no longer explicitly there. But then you get, and performing to get the following equation. So we have a sum over all n, then we have here psi m minus h bar squared over 2m d squared over dq squared psi n times chi n of q plus v of q chi m of q plus sum over all n psi m, then the small h psi n times chi n of q is equal to e chi m of q. No? So that's what I think you can imagine, I mean, somehow where this arises from. No? You just insert this here, then you have these derivatives, and then you multiply this here, and then, okay, in the right, anyway you have the psi's and integrate. Yeah, this d squared over dq squared acts on everything to the right. I mean, these small psi's, they depend also on, must never forget, on the capital Q. So it also acts on here, but also acts on this. Now, this expectation value that arises here gets a separate name. So I call it epsilon E or capital E curled E M N. Depends only on Q, and they are sometimes called the Born-Oppenheimer potentials, because this is a new potential that is added to the classic potential V of Q. It depends also on Q. And just to give you a hint, I will tell you later more. So this is what will correspond to the semiclassical Einstein equations, where you have the expectation value of T mu nu on the right hand side. And you will get a semiclassical Einstein equation as a limit also, like in this analogy. Now often one has a particular case, namely that the psi n are eigenfunctions of this electronic Hamiltonian. Okay, you can do a more general case, but it's not needed. Yeah, but that's also in quantum mechanics often what is of interest. And in that case, then of course this here becomes simpler. It becomes diagonal, because if these are eigenfunctions, then this just gives you then a delta mn because of the normalization of the psi. So we have here then that a e mn of q is just some en of q and a delta. Well, this en depends on q. It's this en times delta. So no sum over n, no sum over n here. No? Then it's simpler. One can define, in addition, also the following important quantity called a mn of q, which is defined as I h bar. And then we have the integral or the contraction between psi m and d psi m n over dq. This is sometimes called a Berry connection, named after Michael Berry, and it will give, when it's non-vanishing, rise to the so-called Berry phase that you may have heard of in quantum mechanics, which is an additional phase for the wave function appears when you have this separation into subsystem and one is adiabatically tracked by the other. Then finally we can define a new momentum curled P, which is the momentum I have not yet introduced, but I introduce it now. I mean the momentum with respect to capital Q minus A, or in indices Pmn is h bar over I, and then you have here delta mn, the derivative, minus, okay, am. And no, nothing. You just in this. If these are operators, then this is h bar over I d over. Oops. d over dq. Yeah, and I think that's clear. It's just identically rewritten. Yeah, if we have this, then we can write this equation, maybe I call it double star, in a different way. And I leave this also as a brief exercise. It's just a bit of algebra, and you don't need to know anything particular to get a result. I think the difficulty is at the level of quantum mechanical exercises. So, oops. Okay, so with this, double star becomes, so brief exercise, the sum over all n, and then we have here the curled p mn squared over 2m plus e mn of q times gn of q plus v of q gm of q is equal to e gm of q. So tell me if I have some, maybe confuse some n or m or something. So that I call the equation 1. We will have two equations. Basically one for the chi part, which is the one of the heavy part, and one for the psi part, which is the light part. Yeah. Okay, it becomes then. So this is still an exact equation. No? I should say that here, this is of course a notation, and it's defined as the sum over k p m p m k p k n. No? And the p k n, they have been defined here. So this now looks like a modified Schrödinger equation for the nuclei. And it is, of course. And you can interpret, I mean, this part here. And part of this, I mean, the A part that is there, because here we have... yeah, those of you who were in yesterday's talk, they perhaps remember this. I mean, this is this A that comes here in addition. So here, the A part, and this here are the back action of the light part onto the heavy part. No? So the electrons are no longer here. This is just for the nuclei. But there's an effect of the electrons because they interact, and this has been encoded here in this term, which is the energy here, and this potential that is here in the P. Yeah. Okay. Now we start with approximations. So far everything is exact and just rewritten. So first, we neglect non-diagonal terms in equation 1. Yeah, I mean, we have here a sum over n, and here you see mn. So there are diagonal terms and non-diagonal terms. What does this mean? This means that the heavy part is independent of transitions between states in the light part. You know? So you can, of course, have electronic transitions from n to m, yeah, and from m to m plus 1, whatever. And if we neglect those in the application, then we can neglect the non-diagonal terms. Of course, this has to be checked whether this is a good approximation, but it works frequently. No? So a first approximation. Neglect the non-diagonal terms. in equation 1, which is the equation just here on top. And then we get that 1 over 2m h bar over I d over dq minus a and n. So that's only the diagonal part of the connection of q squared plus v of q plus en of q acting on Gn of q is E times Gn of q. So this is just a shorthand for En of q. So you see this looks sort of familiar, I would say. I have here this connection. I mean, if you did not have this case, but say discuss connection to coupling to electrodynamics, then you would also have such equations. But here the potential A does not come from the electromagnetic field, but indirectly from the electrons. Now, if this potential was defined here, now if these functions here are real, then A vanishes. I mean, you can just check this yourself, that if this is real, then this vanishes, because you make some partial integration and so on. So vanishes for real psi n, and we assume this to be the case in the following, because I don't want to discuss particular effects coming from A. If not, then, as I said before, A and n leads to so-called geometric phases or Berry phases, which are frequently studied in quantum mechanics and quantum chemistry, and which are measured also. For example, if you have external magnetic field that is time changing, then you get phases in the wave function. But we don't discuss this here. Otherwise, vanishes for real n, assumed in the following. Okay, otherwise Berry phases. Yeah, so what we have here then is then just here, if I rewrite this as the operator version, p squared over 2m, okay, not having the index q, plus v of q, plus En of q on psi n of q is equal to E times. Yeah? So you see the whole effect of the electrons, and later this will be then the effect of the non-gravitational fields, are encoded in this En, which is an expectation value. Now, okay, I call this equation 1. This is because we will also have an important equation 2. And this equation 2 is achieved as following. So we insert again our general ansatz here into the Schrödinger equation, but now without projecting on the small psi. Because we want to get also an equation for the small psi for the electrons. No? So insert now the general ansatz for psi into the Schrödinger equation, no, which is star h psi is equal to E psi, without projection on psi m. Okay, then we also get something that looks a bit lengthy. Then we get then here the sum over all n, chi n of q. Then we have the small h minus, then we have the E minus v of q plus h bar squared over 2m chi n d squared chi n over dq squared. There's the bracket. This is, yeah, that's like that. Minus h bar squared over 2m d squared over dq squared minus 1 over chi n h bar squared over m d chi n over dq d over dq. So this term will become very important later, so I also already draw your attention here at this point on psi n of q, and q is equal to 0. Not also, so we have reshuffled, so the e from the right hand side is on the left, but there's nothing tricky here that has happened here. It's just inserting that ansatz without a projection. And this is still an exact equation. We call this the equation 2. Now, equation 1 and 2 are exact equations, and from which then the approximations are then to which the approximations are applied. Yeah. Okay, what do we do next? Now, I said here at the beginning, we do this mixture of Born-Oppenheimer and WKB. Now, WKB means that you make an ansatz for the wave function that is a product of a prefactor and a phase e to the is, such that the variation of the prefactor can be neglected compared to the variation of the phase. Yeah, either you have learned this in your quantum mechanics course. If not, that's a standard approximation to find then for the phase the Hamilton-Jacobi equation, and then in the next order gives you the prefactor equation. For example, in Landau-Lifshitz volume 5, there's a nice explanation of this, which I have studied when I was a student and learned it from there. Okay, so now perform now for chi n in this equation 2 a WKB approximation. So we make the ansatz that Jn of q is some prefactor, and then we have e to the I m Sn of q over h bar. Yeah, okay, usually this is a redefined S. Yeah, of course, this is the action, but I mean, of course, I have reasons now to extract it. So the dimensions are correct, it's just that you redefine here this S. Okay, this is just an ansatz, but what does then WKB mean? Now we address attention here to this term, here the second derivative, and insert this here and look what happens with this term when we do the WKB approximations. So we get then from this that d squared chi n dq squared is then, yeah, it's just straightforward calculation. I don't have to say much here, plus 2I m over h bar dCn over dq dsn over dq chi n over cn minus m over h bar squared dsn over dq squared chi n plus I m over h bar d squared sn over dq squared chi n. Okay, now you see here the occurrence of this mass m at various places here m m m. So okay, in WKB often you say h bar is small, but you can also in this answer say that m is large. And also this corresponds to the idea of the Born-Oppenheimer that the mass m somehow is large, which is the mass of the nuclei. So we say that m is big, or what we mean is that we want to neglect some terms, so we only keep the dominant term here. You can take this as a definition of WKB here, and you have then this dq squared, so approximately minus m squared over h bar squared d as n over dq squared chi n. So this corresponds to the usual neglect of the derivatives of the prefactor and also of the neglect of the second derivative of here. Yeah, I mean these derivatives are neglected of the prefactor in the usual language, and this higher derivative of s are neglected, and the lowest derivative of s is kept. That's how we define usually WKB. Now, maybe I will. So, I mean, if I have the Pn, I mean the momentum with respect to Q, capital Q, but now acting on chi n. So this is h bar over I d chi n over dq. Yeah, so I give it this index because it refers to that state. So this is approximately d m as n over dq chi n, and this is just the classical momentum. No? Usually you have then the momentum defined from the action as a derivative with respect to q, and we have here m times s, so that's the action. So that is here the classical momentum. And from the above equation here, I mean that we can then find the a classical equation in quotes. So you get then here Pn squared over 2m plus v of q plus En of q is equal to E. Now, so the point is here, that's a quantum equation. I mean, it's an operator acting on chi. But now, if this happens, then you can substitute here the momentum just by this derivative times chi, and the chi then cancels. So you have no longer an operator acting on something. You have, in a sense, a classical equation, but you have this potential, this Born-Oppenheimer potential, which is psi n h psi n. So this is what you get. So you have the classical energy equation modified by an expectation value that comes from the underlying quantum theory. So that is what you get. It's also called that this is the Hamilton-Jacobi equation now with back reaction, or I call it back action because reaction is back reaction is a double word. So this is the Hamilton-Jacobi equation. Hamilton-Jacobi equation with back action. And this corresponds then, or will correspond then, to the semiclassical Einstein equations with, on the right-hand side, the expectation value of the energy momentum tensor. No? So this here will correspond to, okay, psi t mu nu operator psi in the Einstein equations. Now it's time to introduce time, and because you have not yet seen it. So now we are at the level of the Hamilton-Jacobi theory, and we can introduce a time parameter t through the usual Hamilton equations of motions. So introduce a time parameter t via Hamilton's equations. Okay, you know Hamilton's equations, so these are equations for P and Q. So we have d over dt Pn is minus d over dq H classical, and we have d over dt q is d over dPn H classical, and the H classical is without the expectation value, so we have here minus d over dq v of q plus en. No, it's with, sorry, I was wrong. Of course, it must come from this. So it has, of course, this term. And this here is Pn over m, which is dsn over dq. Now you see the t depends on n. What is the n? The n was here, the sum over all n. So it depends on actually in which branch you are of the wave function. No, so that's, I mean, we will get rid of this, but only with some assumption. But so far, we have this time parameter that depends here on the component n. So in principle, we have now so far infinitely many times. Okay, now the last term in the above equation, the one here, this one, oops. No, well, it's a bit high, but I just pointed to you. So this part, this term here, can be written as follows. So above, you can use a color in your manuscript. So it's minus 1 over chi n h bar squared over m d chi n over dq d psi n over dq is then approximately, if you substitute 1 over m d chi n with respect to dq by chi n I over h bar dsn over dq. I mean the wkb here, not that only this first derivatives matters, so you don't have to differentiate here the derivative of that. And then this becomes minus I h bar dsn over dq d psi n over dq. And okay, we have seen here from the Hamilton's equation that dsn over dq is, this can be interpreted as d over dtq. So we have here this here as dq over dtn. Okay, so what do we get then? So we get that this is minus I h bar d psi n over d tn. Now, this looks already familiar. I would say this I h bar first derivative. It's just that here this many tn somehow are disturbing, no? Because usually in Schrödinger equation we just have one t. But nevertheless, we can introduce these tn's, and so the tn's are called WKB time. So if you're in one branch of this superposition, so let us have just the n, a fixed value, whatever it is, then you can interpret this time such that, I mean, in the capital Q space, you consider hypersurface Sn equals constant, and then when this is gradient Sn times gradient psi n. No? So this d over dt can be written as gradient Sn times gradient. So if this is constant because the gradient is orthogonal, runs orthogonal to the hypersurface where this is constant, I mean, it parameterizes here the classical trajectories here in this approximation. Just as a side remark, this is almost the very same formalism that you use when deriving geometric optics from wave optics. So-called iconal equations that you use in optics. Of course, the background is totally different, but you have a fundamental wave theory from which you derive a theory of rays. And here we derive a theory of trajectories of particles from a fundamental wave mechanics. Okay, so we have derived this equation here, and I focus here on this term here, on this term. So we have here that this term can be written. I mean, I hope it's well. I introduced here. I should write maybe here a Tn. Maybe this was your question, that here there is no n. No, so we have this Hamilton formalism, and in WKB we know from quantum mechanics that we are very close to classical mechanics, because somehow we get back the Hamilton-Jacobi theory and the Hamilton theory, and we can use then, if we have, so to speak, we have this here in this approximation, no wave function anymore, just p squared plus v plus e of q is equal to e. And then we can use the classical Hamilton equations, and this defines, in our case, the time. It's not like you do in classical mechanics, you already know what time is, and then you have the Hamilton equations. No, we demand the Hamilton equation, and by this we introduce the time. And then we see this here, I mean here that dt over q. Yeah, this is just a standard, I mean, momentum is mass times velocity equation. But this p is just the derivative here of the phase with respect to q. And I divide by m, so it's just ds over dq. So this ds over is dq over dt. So we have dq over dt times d psi over dq. And so in a sense, I mean, this q cancels, but strictly speaking, it's just gradient s gradient, which is a directional derivative. And Tn is the parameter along this directional derivative. I mean, this directional derivative generates these blue trajectories. And I mean, the tangent in this is just when gradient goes orthogonal to hypersurface S equal constant. So far it's of course an abbreviation. I mean, I have called it time, but of course I have not yet related it to any clock. Yeah, so that's of course one should do. Now, so psi n, so it means that psi n is evaluated along a particular. Okay, you have many, but you choose a particular classical trajectory of the heavy variable. So this means that you have psi von q of Tn and q. Now, originally we have just q, the two q's, but now the capital Q is in this WKV regime, and we can, via this, evaluate it along, say, a particular trajectory. And this then we call psi, oops, I hope you can read it, psi n of Tn and small q. Maybe I write it down again here because I have to hide. So we have here psi n of q of Tn, small q is psi n of Tn q. And this is why we call this TWKB time, because it only comes in this approximation. It does not hold in for general quantum states. Yeah. So from equation 2, then one gets, if one neglects the second derivative with respect to q squared, here this term, if one neglects this term, so from 2 one gets, neglecting 2n over dq squared, and also making use of this equation here. Here it is, this equation here, this, the classical one, this one. So I also use this equation. The following, the sum over all n, chi n, we have h of q tn minus en. So I replace the capital Q with the time in the understanding that we have chosen a particular trajectory along which we evaluate it. No? So the capital Q is all around. No? But in this capital Q, it's like the light rays emerge in geometric optics, and you have one particular light ray that you maybe study when going through the lenses, no? in astronomy or whatever. Minus, and then I use this here, I h bar d over dtn psi n of tn. Okay, so we are not yet where we want at the goal, because this is not yet a Schrödinger equation. Now comes an important point. I unfortunately had to erase this, but we had this ansatz psi is the sum over n. So the whole scheme only works if we restrict ourselves to one component, that is to a product state. Yeah. So that's also an assumption you always need in the Born-Oppenheimer approximation, but it is hardly ever mentioned in the books. It's just done. Yeah, because they say, okay, that's then it follows what we want. But that's an assumption. So, further assumption. Instead of the whole sum over chi n of q, psi n of q, and q, use one product state. Okay, is this a very strong assumption? Well, in the cases that are studied in the textbooks, what usually is behind that is what we call decoherence. That is, we have here a sum, but a superposition of this, the interference term between the is negligible. Those of you who were in yesterday's talk, there also we discussed something like that. But this assumption, which is in most books just done by hand, can be justified, and in more recent years, of course, you have better literature, by investigating the off-diagonal terms of the density matrix with respect to cross terms, and then you have effectively, you can say, you are in one branch. Of course, there may be corrections with other branches, but that's a higher order. So I just mentioned this here. I mean, I cannot discuss it more details. I just want to say that, I mean, all of this works only for a product state, because otherwise you still have the sum of all of this, and you have interferences and Schrödinger cats and all that kind of thing. Yeah. So the last thing is, but that's not an assumption, it's just a rewriting. This here can just be put into a redefinition of the psi in a phase. No? I mean, this is an energy value, and we can put this in the phase of the wave function, like the e to the minus I energy over h bar term times t. So put en dn into the phase of psi n to get, I used then the same symbol, I mean not a tilde or something like that. So, and I skip the n because we are in one branch, and then you get this equation. Okay, so of course you know this equation, but it is here not taken as a starting point for a closed system. It is here being derived as an approximate equation for a subsystem, starting from a stationary equation for the full system. So that's different as maybe most textbook would describe it, because most textbook, at least those that I know, take the time-dependent Schrödinger equation as more fundamental, and then you make this ansatz to get a time-independent. Here it's just the opposite, motivated, of course, by quantum gravity. We take for the closed system the stationary Schrödinger equation, and find then for the subsystem, here for the heavy nuclei, for the electrons, for the light system, an effective Schrödinger equation where time is defined by the heavy system. So in a sense, the heavy system, which is slower, gives you the time with respect to which the light and fast system evolves. So in a sense, the heavy system acts as a clock. Yeah, I write this in quotes. I mean, it's a long way to have a real clock as a clock. Acts as a clock and defines the time with respect to which the light system evolves. So that is the stationary Schrödinger equation for the total system leads to a time-dependent Schrödinger equation for the subsystem. Yeah, this idea is by no way new. I mean, this idea was already presented long ago by Sir Neville Mott in 1931, the one of Mott scattering. Not in this way I have presented, not in this general form. I mean, he just had, instead of, he also not use WKB, he just had a heavy system described as a plane wave instead of this. No? And then there's everything is exact here. So he had alpha particles that were in this plane wave, and then he used them to define, I mean, from the stationary Schrödinger equation, a time-dependent one, then for the other molecules or atoms that interact with these alpha particles. So the idea was like here. I mean, one part of the total system is the definer of time for the rest of it. So that's also what I do not know whether you mentioned this in last week, is in astronomy was called ephemeris time, Ephemeridenzeit, ephemeris time, where so really, I mean, the time inferred from actual positions of the planets and not with respect to an abstract time. Okay, the next thing would be then to take terms of order m into account. And this gives then, in the spirit of WKB, an equation for the prefactor. That's the next order, or the next order in the H-bar expansion, if you prefer the standard way. So terms, so we'll take terms of order m into account. Then in this equation, I hope it's still there, the second derivative of here this, you take these terms here of order m here and into account. You just compare different powers of this expansion parameter, and then you get 2 times dCn over dq dsn over dq plus d squared sn over dq squared cn is equal to 0. And if you have one component only, as we do here, then we have, 2 ds over dq dc over dq plus d squared s over dq squared times c. Yeah, you can also summarize this in the equation d over dq c squared ds over dq 0, and that's in the literature called the WKB prefactor equation. No. Just to give you the connection to the standard things and standard textbook. Okay, now I have talked much about the quantum mechanics, and I think you are here not to learn maybe about quantum mechanics, but to learn about quantum gravity. And so I have now to make the connection here with this. These are also stationary equations, so in that sense are analogous to the stationary Schrödinger equation for the full system. But of course, they are more complicated. But if we neglect issues that have to do with field theoretic divergences and all the other things, we can directly translate, from this example here to this here by just looking what are the corresponding terms. And I think probably it's best if I erase this again, so that you see here the analog. So the formal application to Wheeler-DeWitt equation momentum constraints. Okay, here we had a mass m. To make this formally equivalent, I choose a parameter that I call m squared, but that actually is not a mass squared, but it is often done in the literature like that, which is just this here. In fact, if you look into the units, it has the dimension of a force, but this will not be relevant. And if we do that, then we can write this in the form minus h bar squared over 2 m squared. No, this is now an m squared, also to denote then, because it appears here that this is positive. This is why the only use. So just forget about the m here. It's then the m squared. G a b c d d squared over d h a b d h c d minus 2m squared square root of h3r. So the cosmological constant I neglect for the time being, plus h m orthogonal on. Yeah, I have here a different notation that is popular in this connection y here Bre and cat. So this refers to the non-gravitational field, the standard Hilbert space of, say, the scalar fields. And so what is here then is just the metric, because there we don't know yet about Hilbert spaces. But this here refers to non-gravitational fields. Now, in the above, were the electrons, where we have used this Dirac-Braket formalism. And the second equation is minus 2 over I HAB. Okay, more or less the same. D over D HBC plus HMA on psi of HAB is equal to 0. Okay, so we have these two equations, and now we can compare. Of course, this was erased, but you have seen it, and you have it maybe in your notes. So we compare these equations now with the starting point, the stationary Schrödinger equation, so to see the analogy. So first, this here term, this here corresponds to the minus 1 over 2m d squared over dq squared. Okay, here's the h bar. Okay. And here, this term the minus 2m, this here corresponds to the v of q term. This here corresponds to our small h at the beginning, q and q. And of course this here corresponds to our wave function that depends on q and q. Now, where this here corresponds to this bracket notation, and this q corresponds to the HAB. Yeah, so you see, most work has already been done. If you don't care for infinities and field theoretic subtleties and other nasty things, no, that you would have in principle to do. Okay, so we make the ansatz. Again, we use just one component, because only if we have one component, then we get the Schrödinger equation. So this here is then a prefactor times e to the I m squared s of HAB. Okay, h bar I have here set equal to 1 here, seems times c psi of h AB. Yeah. So that's now this ansatz where this part only depends on HAB, and this here, the small psi without this notation, depends on both. No? And we want to derive an equation for this. This would be the analog to the electronic states, and we will derive a effective Schrödinger equation for them, where the time is given or defined by the heavy part, which is here the gravitational part. So we insert this into this equation like we did before and make this M expansion. And the highest order again is the Hamilton-Jacobi equation like before. Hamilton-Jacobi equation, which here reads, m squared over 2 GABCD ds over DHB ds over DHC minus 2 m squared square root of h 3r. And then comes this expectation value of the matter Hamiltonian here. So that would be then the analog. You see here the classical Hamilton-Jacobi equation, but here from the matter part we have this expectation value. And then of course also the moment. This is from the Wheeler-DeWitt, and the momentum constraints have minus 2 m squared HAB dc ds over dhbc minus psi ham psi equals 0. Now, originally in chapter 4, I explained that the four classical constraints correspond to the first 4 Einstein equations. G00 equal to energy momentum tensor T00 and G0a to T0a with a factor, of course. And in the here you have this in the Hamilton version, and in the quantum theory only the constraints are left. So, which means that in the original Einstein field equations where you have a covariant form, this is really, I mean, this is the Hamiltonian densities. This is what you get from the energy momentum tensor. So this is really what corresponds to psi T mu nu operator psi, which was, if you remember chapter 1 long ago, I discussed semi-classical Einstein equation, which was in the 1916 just given as a candidate for an exact fundamental theory with an exactly classical gravitational field. Had many problems, but you see here, at least it emerges as an approximation in this limit. So you can understand that in a certain limit you have this equation, but not as an exact equation. And then you avoid these problems that I discussed in chapter 1. So in a sense, this is just, I mean, these are just the Born-Oppenheimer potentials. So if one had known maybe at the time when the semi-classical Einstein equation was invented, had known maybe this formalism, then it would be clear that these are just Born-Oppenheimer. And if you do it for electrodynamics, you can also have then the expectation value of the current, the electric current J mu. Okay, then you get also these are the equations. I mean, for the gravity part or for the heavy part, and you get also equations then at the next order for psi. Just translating what I had above, and so you have here h m orthogonal minus psi h m orthogonal psi minus I j a b c d ds over dhb d over dhcd. Okay, this is a different equation acting on psi of h a b equal to 0. And a similar equation for the momentum constraint. Maybe for reasons of time, I don't write it here. Okay, so you see here again, this term that has given us the time, and this was the expectation value that we have put into the phase, or we have redefined psi to put it into a phase. And what we now do is, and also plus momentum constraints, that we evaluate, as above, psi of HAB along a solution of the Einstein equations in the Hamiltonian form of the Einstein equations. What I mean is HAB, the three metric of T. No, it's not just on one, but it depends on T, which follows from, this here follows from, which follows from S of HAB, which is a solution to the Hamilton-Jacobi equation. No? So you have a solution to the Hamilton-Jacobi equation, which depends on the three metric. So you first have to solve this equation here. Okay, I hope it's clear from my writing. Of course, this is this equation here. And if you have S, then you can calculate HAB dot, no? Because this is just, like Q dot is momentum over mass. So you have the HAB dot is the corresponding momentum, basically. So we use for this HAB dot, which is n times GAB CD, ds over dhcd plus 2 d a and me. I mean, you have seen this formula in chapter 4 when I discussed the extrinsic curvature. The extrinsic curvature has to do with HAB dot and then what's basically this here and this term. Now it's just the opposite. We determine HAB dot from this equation because the extrinsic curvature is linearly related to the momentum. So that's more or less the same procedure in mechanics when you do that. Is P over M, and this is 1 over M ds over dq. No? So you see the details are more complicated, but the concepts are the same. The concepts are the same. So if you know where this comes from, then okay, you can understand. It's just that here we have this lapse shift freedom to choose the hyper surfaces. So here, and we have to choose, and they have now to be given. I mean, what we do here, I mean, we really have here one trajectory, I mean, one classical space-time out of the many that come from the solution of the Hamilton-Jacobi equation. And we define then in this particular space-time, which is a solution of Einstein equations, in this limit, this velocity. So we then define, as before, a d over dt psi of t. So instead of the HAB of t, we have then one t, which is of course then a many-finger t in general, but we can define it like that. We integrate here over the x, have our HAB dot, and okay, here I write x of t, and then the functional derivative of HAB of x psi of HAB, no? So that's how we can define it. I mean, this we have the velocity, as we have to choose lapse and shift because we all this comes with a particular foliation and a particular coordinates. Then we get the HAB, and then we can just take the solution along that functional differentiate, and then we get here, or we define it. It's a definition. And then we get, and I insert h bar here, the final result, I h bar d over dt of psi of t is the integral d3x n h orthogonal m plus na hma of psi of t, which is nothing than this the integral over the densities, but this is, as you remember, the total Hamiltonian of the matter fields acting on M. So now we are back to have quantum field theory in an external space-time in the Schrödinger picture. It's not non-relativistic quantum mechanics, because you can also, as we discussed earlier, have quantum field theory in the Schrödinger picture. And as before in the quantum mechanical example, if we focus on a product state and we have this WKB approximation, then we get an effective Schrödinger equation with respect to a WKB time from the timeless underlying quantum theory. So that's the emergence of time from timeless quantum gravity in this formalism. And this is, of course, very, very central here to this. I mean, at least so formally, if you don't take care for infinities in these functional derivatives, then that gives you back the old physics quantum theory in a classical background that satisfies Einstein equations. Yeah. So the final thing is, in the last very few minutes, that of course because this is an approximation, so you can go further on and discuss higher corrections. We have neglected these higher M terms, so you can go on. I mean, this is what we in our group in particular have discussed. So the next order would give corrections proportional to 1 over m squared. No? Well, here I have the m squared. If I used here a m, then it would be 1 over m, but basically then this will then be also play the role of the Planck mass squared. No? If you take the h bar in addition to this definition here, and some c's in this equation. And of course, time does not allow me to make a very detailed discussion of these terms in the book, but I think most recently also we wrote a review where we calculated observable effects from these terms, which I maybe recommend here with Leonardo Chatenier, okay, myself and Paulo Moniz. And this is in classical quantum gravity, volume 40, 2023 and 22301, or you can also find it on the archive under the number that I write down. And there you can find details about observations that in particular quantum cosmology, using these terms. Just a final remark. I mean, I have not discussed early universe here. I had a separate lecture course on early universe. So for those who attended that, they have heard about inflation and about the cosmic microwave background and the anisotropies of the cosmic microwave background. So because this is independent of what I do here, just give you some results, and it's certainly of interest those of you who know that. I mean, for the CMB, I mean, there is this curve that you have been seeing of the anisotropy. I don't define it now here in all detail over the multipole, so small l as big scale and big L as small scale, and it looks something like this. You have this peak, these oscillations. And small l corresponds to big scales, and this is also where quantum gravity effects are bigger because they come from the earlier phase of inflation, if you do. No? And so without the corrections, one gets a power spectrum from the wave functions that I mean, one can solve this equation here in cosmology in a certain context with inflation, and then calculate from this 2-point functions. And this gives you the power spectrum that people also in cosmology usually use, and also that the Planck satellite has measured. So two power spectrum. And just give me let me only give me of the density perturbations. There are also the so-called tensor modes, which are the gravitational waves coming from inflation. But I have no space to this here. So we have here PS0. So this is just from this equation. Depends on the scale, on the wave number, is HTP squared times 1 over pi epsilon. Okay, what's that? That is the Hubble parameter of inflation, which is roughly constant. And TP is the Planck time. Now H has dimension 1 over time, so this is dimensionless. This is the number pi, and epsilon is the so-called slow roll parameter from inflation, which you can just take as a parameter from the early universe, a dimensionless parameter. And with corrections, that's what we did. I mean, with corrections, you have PS is of k is approximately PS 0 of k. I mean, this one, and then you have here 1 plus 1 plus 4 pi over 3 HTP squared k star over k cube times, okay, then come some numbers, they are numeric numbers, minus 2 ln of minus 2 k eta. Okay, I have to explain what that is. Sorry for that, but the space is limited. So you see here there is a correction term here, and we have here a 1 over k cube correction. This is the scale. The k star is a so-called pivot scale. This is a certain scale that comes from the observations and sets, so to speak, the comparison with the observation. A certain size in the spectrum where measurements are made of the amplitude, and so we normalize with respect to that. But you see that here explicit k dependence comes, and there's also a logarithmic term. So eta is the so-called conformal time of this quasi-de Sitter space that we use in inflation. So that's only of interest. I mean, if you have heard about this, for the others, I want to emphasize that yes, one can calculate effects from this framework without cheating. I mean, without putting infinities under here the table, because of this semi-classical approximation, because they are not in the full theory, and also in these applications, these fluctuations here are very small, so they don't interact with respect to each other, so you can treat each wavelength separately. So so you're back from this to quantum mechanical Schrödinger equations for each wave number. This is why you can do these calculations without really having to go into regularizations of infinities, which is a nice thing. And to come up with concrete numbers. Okay, this number, it's too small to be seen because, I mean, this can be estimated to be maybe of the order of a 10 to the minus 10 correction. I'm afraid that even the excellent Planck satellite that flew 10 years ago is not able to resolve this precision. It was also not expected because quantum gravity effects are small. They would be bigger and measurable if inflation had happened closer to the Planck scale. But from observation, one gets that inflation is maybe 10 in energy, 10 orders of magnitude below the Planck energy. And this is why the numbers are maybe of that type. But in another world with inflation closer to Planck scale, then these effects would be bigger. Then you could zoom in here. So we predict here an enhancement of power at small scale. Anyway, the errors here are big. And so it's just to show in principle that you get observable effects. And this is what we should all do. I mean, we should also think about other situations where we perhaps find an effect that is really observable, and we can test the theory. Yeah, so far for today, and so far also for chapter 5 and quantum geometrodynamics. We have 3 sessions left. So next week we do again canonical quantum gravity, but in another formalism, briefly review, that is called loop quantum gravity, which has been fashionable in the last decades. There we will also see constraints, but they look a little bit different. And the remaining 2 are then really 2 sessions are devoted to the real universe, in a sense, black holes and cosmology, to see how we could apply all of this for black holes and for cosmology. So, okay, thank you for your attention. See you next time.